All right, and here I am, um, just making sure everything is set up. I'm going to be continuing with trigonometry. I've already done a couple of streams today, math streams. So here we go. Good. Okay, sound is good. And hi in the chat. We're doing algebra and trigonometry right here. Okay, this is part of OpenStax, and this is part of Creative Commons, so I highly recommend getting the book. But if you want to download it and see it right now, just go in the description of the video. All right, I am continuing section 1.1, and we are going into 53 is where I left off. Okay, so let me start a new thing here. That's from a previous stream I did. Anyway, yeah, in case you're wondering why I do all this, it's to improve my own math skills. Math is my major, and the greatest reward for getting better at math is being able to do more math. Okay. Okay. Okay, Fred made the mowing lawns. Hey, that's me. That's literally what I do. I mean, not just that. I'm a landscaper slash handyman. So, yeah, that's funny. And I go to university for pure math and computer science. Although this semester I'm on break to focus on work. Okay, so he spent $10 on MP3s. Okay. Um, okay. Puts half of what's left into a savings account. So that's 30 divided by 2, which is equal to 15. Okay. So right now we're 15 left. All right, and then okay, he gets another 5 for washing neighbor's car. Huh. This guy does not know how to be a good businessman. If you run your own business, you really have to be good at a lot of different skills. And this guy's clearly underselling himself. He's currently at $20. Okay, so they wanted to see the expression for all this stuff. So we're going to say this order of operations. So 40 minus $10. And then we can either go divided by half or times 1/2. Doesn't really matter. Let's see here. Let me think about this for a minute here. This gives us 30 divided by half plus 5. Right. Divided by half plus $5. Or we could also write it like this. Now notice that I threw the parenthesis, PEMDAS from previous video, parenthesis, exponents, multiplication, division. Remember that order. Either one would work. All right, well. So now we go to the back of the book and see. As long as we have the same answer and it's not a coincidence, but we actually followed similar lines of logic, then my answer would be acceptable. Yeah, that's fine. That's correct. So just to be clear, like the difference between these two, these are the same. They went with the bottom version, but you can do this. You can pull this and make it a 1/2. So they actually wrote it like this: 1/2, 40 minus 10 plus 5. That's exactly what they wrote, which again is the same thing here. Putting on either side doesn't really matter. Yeah, we do left to right, but in this case, you would still get the same result. So it's fine. Okay, good. It was 53. Let's go to 54. Sorry if I sound a little gravelly. It's been a long day. So I work during the daytime, during the daylight time. I actually worked till 7 today. Use my lamps to continue working. Anyway, let's see here. And this is my third stream, I think, today. Yeah. All right. Right. 55. Okay. I'm gonna try to pin this. Okay, here we go. 55. According to the US Mint, the diameter of a quarter is okay. Okay. The circumference of the quarter would be the diameter multiplied by pi. See, the circumference is going to be 0.955 pi. Okay? And that's correct. It's diameter times pi if you want to get the circumference. That's the formula. Is the circumference of a quarter a whole number, a rational number, or an irrational number? Okay. Right. So there's a thing, this goes back a couple hundred years, called squaring the circle. And the idea was, can you take basically it's geometry, and they try to turn the circumference of a circle into a square by like it's like, I believe it was like a circle in a box or something like that. I forget exactly how they did it. I think squaring a circle looks like this. I'm gonna look it up in a second. I'll tell you. I think they go like this, and they try to square this by and that sets up your dimensions, and then you want to try to unpackage the circle and create a rational a fraction. Let me see here. Don't quote me on this just yet. Squaring the circle. The perimeter of the circle is equal to the circumference of the circle. And the perimeter of the square is equal to the circumference of the circle, or the square and the circle have equal areas. Now again, this is very nutty stuff. What it doesn't actually work, and I'll explain in a minute. Here we go. Okay, that's slightly incorrect. Here we go. This is how you do it. The description was correct, but this is what squaring the circle looks like. All right, we're just going to give you a bit of a history lesson, why this matters. Okay, I'm just looking this up real quick. This is a Greek mathematician's prose. This is on Wikipedia. Okay, the difficulty of the problem raised the question of whether specified axioms of Euclidean geometry, since the line squares imply the existence of such a square. So, um, yeah, it was proven impossible in 1882, and that proves that pi is a transcendental number. And there's your answer. Pi is transcendental. So yeah, it's in the real set, therefore it is irrational. Now, we don't actually need this, but let's just do it like this. By if a teacher saw this, they would probably be impressed. But you'd have to explain it what this means, or at least to give them a brief overview of what squaring the circle was meant to have been. Okay. Here we go. Okay. The circumference of the quarter will be the diameter. Is the circumference of a quarter a whole number, irrational, or irrational number? Is irrational. Now, if you take any number and you multiply it by an irrational number, the number would still be irrational. And the reason being is that, like, see, pi has no end. You could multiply it by whatever, but there's nothing that you can stick that to. So, like, let's say here 3.14159. Let's multiply it by a whole number, by 10, which now moves it goes 31.4159. You multiply it by 2, 4159 times 2, and that, again, you can get an approximation, but the actual numbers, you'd have to multiply by 2 every digit in the pi line, which is impossible. So, like, if it suddenly terminates, you do it on your calculator. You do 2 pi, which is a full circle. Then what would happen is, actually, again, if you wouldn't get a whole number, your calculator terminates after a certain number of digits, but pi is irrational, basically. That's all we were going to try to say. And any number, any Okay. Any number that is rational. Rational means that it could be a fraction, but it terminates. Let's say 1 divided by 2, you get 0.5. It terminates. It could be a very long string of numbers, but if it terminates, it's a rational number. If the numbers go on forever, then it's irrational. Just as you can't square the circle, and by the Lieberman Weister Weierstrass, by the Lieberman-Weierstrass theorem, pi is transcendental and is rational. Okay, so that answers that. 55. It's probably a little more than they were expecting. Let's see what they have to say. Irrational number, yeah. Okay, I went a little over the top, but The box means end of proof. Hmm. See, it's more fun for me to like start doing proofy stuff because that's what I study. I'm a student. Okay, I don't take it as anything, but I love all forms of math. I love doing it. Love studying it. Love polishing up my own skills. Okay, write the equation that describes the situation. Then we're gonna solve for G. Hmm. And well, the other thing is when you say irrational, it means also non-repeating. So if it's like 0.333333, I believe that's still considered a rational number. So non-terminating, non-repeating makes it irrational. And non-repeating doesn't mean it wouldn't have repetition within it. You could have like a set of threes, or four sixes in a row. But what it means is that there's no greater pattern that keeps repeating. No 5 or 6 or 10 or 1,000 digits that keep repeating in a row. Like you can go through one cycle, then you go through another cycle. That's not what we're talking about. Okay. Right. 57. 57. For the following exercise, consider the scenario. There's a mound of G pounds of gravel in a quarry. Okay, I'm familiar with this stuff. Throughout the day, 400 pounds of gravel is added to the mound. Two orders. Okay. Okay. All right. Two orders of 600 pounds are sold, and the gravel is removed from the mound. At the end of the day, is added. Not that day. Airbrush the per. Okay. That day is added. Okay, now we're gonna say 2 times 600 pounds minus. Okay. Okay, and final tally. We're gonna solve 1,200 of gravel for G. A minute. Okay, 1,200 pounds remains. So let's solve this. This shouldn't be too bad. So first of all, write the equation. So we're gonna say G plus 400 minus 2 times 600, and then is equal to 1,200. Okay, now if we were doing like physics, we would probably write LBS, LBS, LBS everywhere for pounds. Okay, read it one more time. Two orders of 600 pounds. Okay, let's solve this. All right. So we're going to say G, okay, plus 4. I'm going to rewrite the equation because I need the first one for the answer. Minus 1200 equals to 1200, okay? And then G minus 800 equals to 1200 plus 800 plus 800. G equals 2000 or 1 ton. 2,000 pounds. Mm-hmm. Yep, that's correct. Okay. Good. All right. For the following exercise, solve the given problem. There we go. Okay. Okay, so we have 1.1, and we are at 59. Okay. Ramon runs the marketing department at his company. His department gets a budget every year, and every year he must spend the entire budget without going over. All right. If he spends less than the budget, then his department gets a smaller budget the following year. Oh, great. At the beginning of this year, Ramon got 2.5 million for the annual marketing budget. He must spend the budget such that 2,500,000 minus x equals 0. What property of addition tells us what the value of x must be? I think it's associative property. Right, because we want to make it, yeah. X equals to 0, or we can also do this. Plus negative x equals to 0. We can do that. Okay, I would say associative property. No, hang on, that's not correct. Okay, so hold on. Every real number has an additive inverse denoted as a minus. Oh, right. That makes sense. So by so we're adding the inverse of it. And when you add something to a formula, you have to add it to both sides. You can't just do it to one side. So you have to add it to both sides, which is equal to there, by the inverse property of addition. So that's the answer. Okay, technology. For the following exercise, using graphing calculator software X. Round the answers to the nearest hundredth. Okay, sure. And the point is to teach you how to do this stuff. Well, I guess I should probably put the equation on the screen. Okay, so I'm gonna solve the interior of it. My calculator doesn't have a backlight, so I'm gonna say 0.5 squared because, right, but it doesn't matter if it's negative or not. I'm squaring it anyway. So 0.5 squared is back to 0.25. So this becomes 0.25 x. Now remember, because we're using, it doesn't matter if it's positive or inside. If you square it, it becomes a positive number. Minus 7.2 equals 9.9. Okay, so then we're going to say 9.9 plus 7.2, which is equal to 17.1. Additive inverse property. So 0.25x is equal to 17.1. And we're going to divide that 0.25. Okay, and that's going to be 0.25, 68.4. Okay. They said to round it to the hundredth. Nearest hundredth, okay? 4D. 68.40. Okay. Make sure I got that right. Yeah. Okay, I like this. They tell you to round it to the nearest hundredth and then just leave it at the 10th. That's nice. Now, I mean, for this kind of a class, it's going to be okay. If you were in a physics class, the teacher would have your head. Okay, you absolutely. They tell you round it to nearest hundredth, and it's just zeros. You do that, and the reason why that's important is, in one equation you just might end up with a zero, but on the subsequent one it might be of a different. It might be in the hundredth, but this one, if you live in the tenth, and then you multiply it out, you could easily confuse yourself or whoever's trying to read your notes, because it could suggest that you rounded it off. You don't know. That's why I put the zero. It suggests if you did or did not have to round it. Because technically, you could do rounding, but it doesn't matter. Let's continue here. We're not in a physics class here. This is just me studying math toward my degree. Long-term project. Terms the multiplicative inverse of a rational number is rational. Multiplicative inverse. Right. So let's take a number. Let's just say 4. And then we're going to multiply it by multiplicative inverse or reciprocal. Yeah. So multiply by reciprocal, which is equal to 1. 5 times 1/5 by its reciprocal is equal to 1. Yes, it is always going to be rational. Okay, so not only that, it would be 1. Is also rational. The multiplicative inverse of a rational number Although, hold on. This is rationals. We can also have fractions. So hold on a minute. Let's just do this. Times 1/4, which is equal to 1/4 times. This all gets flipped times 4, which is equal to 1. Yeah, that is correct. Mhm. Yes, book agrees. And 65, determine whether the simplified expression is rational or irrational. All right, let's just continue down here. 67. All right. So we have to multiply. We're going to go left to right. Let me just think about this for a minute. 20. 4 times -20. Now, here's the thing. Notice how there's two negatives. There's a -1 right here, and there's also this one here. Uh, it doesn't matter. You're still going to end up with a positive result because whether you multiply it like this and then you add the negative, or if you multiply the whole thing, you're going to still end up with a positive number. Let's look at that. -18. 4 times 5 is 20. Times -1 is -20. Minus the negative makes it positive. It's irrational. The answer is irrational. Root 2 is irrational. Okay, irrational. Okay. All right, and 69. Okay, it'll be 69. Wait a minute. I see what I did there. Okay, that's better. 67. The division of two whole numbers will always result in what type of numbers? Okay, so notice the catch for, what do you say, always? So that means we can use any example. The division of two whole numbers, it doesn't say the same, it just says two whole numbers. So, it'll be a rational number. So let's say here 4 divided by 2 is equal to 2. We're going to say, let's try 3 divided by 5. 3 divided by 5 here. 3 divided by 5. Okay, how about 22 divided by 7? Now that's a close one. 1, 2, 3, 4, 5, 6, 7, 8, 3.14. That's a close approximation of pi, 22 over 7. Two whole numbers will always result in what type of number? Well, the keyword is always, so that means it must be, I would say rational. That's it. That's what I think. Yeah. And here's how I deduced that. I mean, they said always, so that means I just immediately went for examples that favored my preferred outcome, which was the B to make it rational. So I took some simples. 4 divided by 2 is a whole number and is a rational number. Now, it's also a natural number and is also an integer. Now, however, obviously, you could have any number of rational numbers, sorry, a number of whole numbers that are negative. So you would, in other words, whole number is not a fraction. So if you have a negative number, we knock out the naturals. And then the other thing about it is that, like, the 7 over 22, it just gave me a fraction that, because you have a fraction, or any fraction really, 1 divided by 2, it's a fraction. If you have a fraction, then it's a rational number. And if it's a non-terminating, non-repeating fraction, then like pi, then that's irrational. And the irrationals are in the real set. And each set is like a nested doll. Naturals, followed by the integers, followed by the rationals, all live inside, along with the irrationals, inside of the real. Okay, and that was the end of this section. I should get some sleep. Sound very groggy. I'm looking at section 1.2. Mm-hmm. In what regard would that be the same? Oh, okay. No. 2 to the 3 is, let's see here, what is the purpose of the expression? 81. Okay, it's 2. So for the expression, yes. Yes, this is good stuff. Okay, yeah, this is going to be a fun chapter. I like 1.2. Hmm. What time is it? 11:48. Yeah, I should get some sleep. This is a fun chapter, and I guess I will have to do that next time. All right. Good night, everybody.